Hello everybody. Today I'm going to introduce you another tool of the CoastalHydrodynamics set, which you can find on GitHub on CoastalHydrodynamics, Ale Rovere / CoastalHydrodynamics. And this is the wave data downloader. Let me click on it here, and this is it. So you can download the code that I'm about to show you from here, and what you will get is basically this Jupyter notebook that you can run directly in Google Colaboratory. I'm going to show you how to do that, basically to download virtual wave data from a virtual buoy from the Copernicus marine. The source, the wave data source, I'm going to show you this one, is this one, the global wave reanalysis from Copernicus. And you will need a subscription to this system. It's very easy. You just go into register and you register your user. They will give you a username and password, and you will be able to access the data through this script. So to run the script, you will have to create a free account to the Copernicus Marine Service, and we will work with this data from Lo Chun et al. 2021, which is a global reanalysis from wave data and model hindcast from satellite altimetry. Good. Without further ado, I'm going to show you how this script is working. I called it Wave Data Downloader and Analyzer. This is basically a small script that allows you to get the data from an area of interest and download the data in a netcdf format. And from the netcdf, you can interrogate one point, which we will call your virtual wave buoy. So this is where the waves are going to be exported for you. Very nice. So we are in Google Colaboratory. If you want a bit of a more simple approach or simple introduction to Google Colaboratory, you have my very first video, which is here, which I did for the wave run-up model, where I explain a little bit better how to use it in Google Drive. Basically, you will have to upload the folder you download to Google Drive and then open in Google Colaboratory this IPYNB file. Okay. So let's proceed. I will first of all install some dependencies. Now in Google Colab there are many libraries that are already installed, but not all of them are installed, so I need a bunch of them. Copernicus Marine, which is the library given by Copernicus Marine to interrogate their data. Windrose to make wind and wave rose data. Cartopy for maps, and matplotlib for a bit more advanced plotting capabilities. Then I download all the libraries that I need. It took a second, and then I mount my Google Drive here. So I basically, well, it's already mounted here, but what I basically do, let me show it to you, is I make sure that I have my Google Drive mapped here, and be very careful that you have to give here the path where you saved the script. In my case, is this one, CoastalHydrodynamics. I go here, I copy the path, and then I paste the path here, so you have the correct folder where you're working in. It will create two folders, output data and output images. Everything you see is going to be saved inside those two folders, which I'm showing you are here, output data and output images. And this is where I have my download waves Copernicus data. Now I'm going to close this one. Good. So the first thing we do is define and analyze, visualize the area of interest, the site of interest, and the virtual buoy. So the area of interest is basically a rectangular area from where we will download wave data. And the site of interest, I define it as the site, the coastal site, which I want to investigate. And the virtual buoy is a place offshore from that site where the waves offshore are going to be extracted. Now, the script now is asking you for a bunch of things here. So the bounding box of the area of interest, the coordinates of the site of interest, which today for us is going to be Cape Canaveral, just because it's a famous place. So I just thought to do some wave modeling there. Later on, I will have a wave model on Cape Canaveral. So I'm gonna have to enter longitude and latitude in WGS84, target longitude and target latitude again in WGS84 for the virtual buoy. To find these coordinates, I often rely on an external tool which is called bboxfinder.com. It's very easy to use, so you just go to bboxfinder.com. For example, in my case, I think Cape Canaveral is here. You draw a more or less wide area where you want to have data. Of course, you're not going to have data onshore, but this is the area where you get the data. And then from down here, from the box down here, you get the bounding box coordinates that you can then insert down here. Okay, so a couple of considerations on the area. The area of interest bounding box must be at least, let's say, 1 degree by 1 degree, because I think, if I remember correctly, the resolution, yes, it's written here, actually it must be at least 0.5 degrees by 0.5 degrees, because the resolution of the Copernicus model is against 1 over 5 degrees. So at least you need to have some data inside there to make mapping products, etc. And it shouldn't be too big, so I would at least make it, you know, maybe 1 or 2 degrees, not more than that, because Google Colaboratory has a limit on what it can do in terms of data and RAM that it can handle. So I wouldn't make a huge area. Just make it 1 or 2 degrees by 2 degrees maximum, and you should be fine. So I run this one, and I do get a plot. This is cartopy, a plot of the area that I want, where I want to extract the data. So Cape Canaveral is here. My virtual buoy is right offshore Cape Canaveral, and I can basically go on. The next one is going to be downloading wave data for the Copernicus Marine Service. This is where you need the login. I'm not going to run it because I already ran it and downloaded it. It takes 5-10 minutes, but I'm going to walk you through this. First, you make the Copernicus Marine login. It will ask you your username and your password. You insert them, you press enter, and then you can go on. And then you switch to interrogating the Copernicus wave data set. So with the data you gave before, with the coordinates you gave before, it will extract the data from January 15, 1980 to January 15th, 2023. And it will only extract wave height, significant wave height, wave period as spectral peak, and mean wave direction. So there's many more variables inside this data set, but we only take those because otherwise the size of the file is going to be huge. Once you are done with inputting your username and password, you just click here, and it will show that it's downloading things. It will take about, let's say for me, on a good connection, it took about 5-10 minutes tops. So that's what you are going to get. Once you're done, a file will be saved into your Dropbox folder. Let me see if I can, into output data, and it's this one, Cape Canaveral. Well, it's gonna be called as your site of interest waves copernicus.nc, which is a net CDF file. So we just run this, and the file opens up. These are all the properties that you have in the file: latitude, longitude, and time, of course, and wave height, wave period, and wave direction. This is basically all the attributes you need to do. Don't forget to cite these tools, or these data, if you use them. So you have all the citations in my code as well. The first thing we do is we compare the average and extreme wave conditions for the entire area. So we're making two maps, basically showing, let me run it, basically showing the average wave conditions in this area for each cell, and the top 10% waves for this cell. Let's see when it's done running. This is how what it will show. It takes a second. This is because it's analyzing the data and getting cartopy. There we go. So you have basically on the left-hand side the average waves, wave direction, wave height, and wave period as contours, and the top 10% highest waves. So you see that the top 10% highest waves get on average above 3 meters, something like that. Okay, so this is actually quite interesting to have a direct visual comparison between what we could call annual fair weather conditions and the the storms in the area. I think this is basically an average in this area of hurricanes plus, you know, extreme swells coming from afar. Good. Now we turn to the virtual buoy. So this is the virtual buoy that we have here, and now we turn to data from that virtual buoy. So now what we are gonna do is extract a time series from that location that you have here on the virtual buoy. Okay. Okay. So this is a time series at the virtual buoy of significant wave height and peak wave period. And you see that we get up to, let's say, 10 meters even, and up to 20 seconds period, right? About the directions, we use a wave rose. So we move on wave rose diagram at the virtual buoy. So we run this, and it will calculate a wave rose. This is the direction from which the waves are coming. If you're standing on the coast, you see waves coming at you from, say, east, south, southeast in this area most often, and this basically matches what we see in the maps. Okay, so you have, say, east roughly on average, and then you have a bit more content in north, east, and northeast for the highest swells. Okay. Then we, if we want to use this data somewhere else, we just export them. So they're gonna be saved as a CSV in the output data virtual buoy wave data. So you have all the data from the virtual buoy saved in a CSV file, which is quite easy to use, easy to import in other programs. But then I was thinking maybe you want to have a quick and dirty way to select periods, or select a swell, for example, in this area. So I made up this script using plotly to basically explore the data and extract a particular period. So you run this cell, and what you get, it takes a second because it's loading lots of data. Okay, what you get is basically a selection tool. So you see we have our 10 meters swell, but if I wanted, let's take a swell for 2004, and I wanna see this one, for example. Okay, so we have decent period, decent swell, and then I put here the dates: September 3/09 2020 2004. Okay, to September, this is about September 6 or September 7. Let's make it 7 of September 2004. Okay, so from the 3 to the 7 of September of 2004, not 004. Okay, from the 3rd to the 7th of September 2004. This is what we want to have, and we press on confirm, and you see that we extracted 33 records, so 33 points of wave data. And then we export it to CSV, of course. So we have another CSV called select your virtual buoy data, and these are the dates in which we selected the virtual buoy data. So this might be useful, and it will be useful if you continue this series of example into making an X-beach model, for example. You can use this output as an input to X-beach. A bit of visualization of the waves then. So I started to think about how do we really characterize extremes in this area. There's many different ways to do that, common to coastal oceanography. But first thing I did was basically show the 90, 95, and 99 percentiles on a map. So you see that the 90th percentile, so the 90th percentile storm significant wave height is about 2.25 meters, and the 99th percentile is a storm which surpasses 3.73 meters. So storms surpassing in wave height 3.73 meters are really at the top of the storms in this area. And now then I wanted to visualize on a graph like this one the storm events. So I wanted to see where the storm events were falling. To do this, so I basically selected and it's here in the configuration. I basically selected the 99th percentile, and I set that a single storm is considered a single storm where there is one peak every 148 hours, which is about which is 4 days. Okay, you can play with these numbers. You can put 0.95 here and 72 hours here. Depends how your area is. But for this example, I will keep it as it is. So I just click in here, and you will see that we have all the identified storm events of height above 3.73 meters that are separated at least by 148 hours, and it identified about 153 storms. Now here there's many things that can be done. This is very simple. Probably a better peak analysis would be beneficial to this, but for an example like this one, it's okay. So we can just move on just to understand the concepts. Okay. So then we try to plot these storm events on top of the entire wave data, and it's going to take a bit, but you see that all the lines here are single storms that are hitting the area of Cape Canaveral in this case throughout time. Okay, so these are all the storm events which are happening from 1980 onwards. Now I use these storms, this record of storms, to make some statistics. So first of all, I want to know how many extreme storms there are per year. This could be an indicator of, let's say, return frequency. So I press here, and you see that you have a fluctuating number of storms. There are years with more storms, years with less storms. 2020 and 2001 seem particularly bad from the point of view of storms. Again, this might change according to how you select the definition of storm and the peak, especially the peak threshold. So let's not take it at face value. Let's not take it too religiously, but this is a way of visualizing things. And then, still with the same caveats, we can go into the return times estimation. So the probability that a particular storm will happen every year. There are different ways of doing return time. Here I basically show two. One is the Gumbel distribution, which is a very classic approach to model annual stream, and then the generalized extreme value distribution, which is a different way of estimating return level. And in the Gumbel, I also added a 95% confidence. So here it is. I basically run this code where I obtain the return level data from the Gumbel fit in blue and from the general extreme values fit. You see that they are different. Yes, I usually prefer for wave data to use the Gumbel, also because we have a bit of an estimate of return times. But you see that basically we have, let's say, a 10-meter storm, which happened, I think, only once in our data set, as a return period of about 100 years. So this means that the probability of this storm to happen is 1 in 100 years. So it means that the probability is 0.01 that it happens every year. Okay, it's not that it's not, the return period doesn't indicate you that a storm like that will come only 100 years from now, but only every 100 years, but it has a probability to return 1 over 100. Good. Now I did some other analysis here. So I was interested in see the temporal patterns in wave height, period, and direction to basically have a visualization of climatology, basically, so seasonality as well of the different wave conditions. So I run this cell, and here we see that, you know, there is a decrease, of course, of significant wave height, and in part also period, but it doesn't show very much during the summer months. And then you have higher wave heights as you get into the hurricane season and into the winter season, where probably Atlantic storms kick in. The period, the month with the highest period is probably September/October, November. This is hurricane season. That's not unexpected. And you see that basically the annual frequency of wave direction and our wave buoy, which is rather coastal, is basically northeast east, which is basically you know, perpendicular waves to the shore coming from the ocean. The next thing I did was going into investigating a bit the monthly anomaly of significant wave height and period. And basically here I compare each month to the long-term climatological trend for that month. So it means that I'm trying to understand if a particular month within a year is stormier or it has higher significant wave heights and periods. So I run this, and here you need to interpret this. So red is where you have higher waves than or higher periods than the climatological mean for that month. And you see that, well, in the last, let's say, the last 10 years, 15 years, something like that, you see something coming out a little bit more on the red. Of course, you have a bit more red on this part as well. You see a bit an increase in the wave periods, especially in the hurricane months. So these are all considerations, which of course are only for one buoy, one place in the Atlantic, but you can make this these sort of considerations to have an idea of what's going at your buoy through time. Okay, and then I did a climate strip plot. So this is not really climate related, but it might be, just to see how the wave conditions have changed over time. Basically averaging making the monthly averages of significant wave height and period through the various years. So if I run this is what I have. So this is time from 1980 to 2023. And you clearly see, especially in the significant wave height, the seasonality. It goes winter, summer, winter, summer. Blue is of course summer, and then you have the red is the winter, the starting of the hurricane season, etc. You see some bit of change in the more recent periods. You still see some change in the 90s. I mean, you still see some bright red periods in the 90s. It looks like something is happening with the wave period at our buoy as we progress through time. So we have probably higher periods, and this is something which was coming out as well before, as we progress in time. Again, this could be climate related, but it's one buoy, so it's one place in the ocean, and this is not significant in terms of the general trend or anything else. I mean, this is just an observation. Let's not make the mistake here. Although we know climate change is real and climate change is happening, and climate change is also affecting waves, wave height, wave peak, and also wave direction. But let's not make the mistake of making big story out of one buoy. But this is a way to visualize it, and this is a way to think about things as we do data science. This is it for it. So if you want to use this one, again, go to the wave data downloader. In my GitHub page, you have everything you need to get started here. And the only thing you have to do, create your own account at Copernicus. Do not forget to reference the data source, the global reanalysis of Copernicus, and the associated paper of Low, Chun et al. 2021. Good. Thank you very much, and see you the next time. Happy wave hunting.